So I'm Gavin. This is my Master in Electronics final project, and for it I made an EEG. So the purpose of the circuit was to take in inputs from these electrodes, well, two of them. One connected to the forehead, which was taking in the main brain signal, and then one connected to the earlobe. And the purpose of that was to have a noise signal. And then those both were introduced into the circuit here. And the first element is a differential amplifier. So what that does is it subtracts the noise from the main brain signal and then amplifies it a little bit. So then what you're left with is just ideally what should be coming from the brain and what composes the brain signals. And so the purpose of this circuit was to try to analyze the brain waves and see what the composition was in terms of alpha waves and beta waves and give a representation of that. So the final output of the circuit was this blue LED shows kind of a measurement of how much beta wave activity there is, and this white one is how much alpha wave activity. So once the signal is just the all the brain waves with no noise, it goes through this, which is a active low-pass filter that filters out everything above 30 hertz. And that's because alpha waves are between 0 and 13 hertz, and beta waves are between 13 and 30. So then what comes out of that is just alpha and beta waves. And then that's taken over here. Well, it splits off, and one part goes over here, and this is an active high-pass filter for everything that allows through everything above 13 hertz. So the output of this would just be the beta waves, and then over here we still have the beta plus the alpha waves. And so this beta wave, since it had been inverted here by this active filter, it goes through just a gain of 1 inverter again, so that it can then subtract with the alpha plus beta waves here in another differential amplifier, so that what you're left with out here is just the alpha waves, and then from here you're left with just the beta waves. And so then the alpha waves and the beta waves each go into, these are both half-wave rectifiers with a capacitor on them, and that allows the sinusoidal wave to be turned into a DC value so that it can go through an LED and give a representation, a continuous representation of the magnitude of that value. And so then you'll see these outputs here. Now, unfortunately, the voltage coming from the brain through these electrodes is not strong enough to activate these op amps that we're using. However, I have a representation here. So this is just a function generated brainwave, which is a composition of many different sine waves of different frequencies, some in the alpha, beta, and then above ranges. And so when I start this, then you'll see here we have blue and white are both lit up, so there's alpha and beta waves in this, and they're both of that magnitude. And so if we look at the scope, this is kind of the blue is the beta waves, and the yellow is the alpha waves, and you see the alpha are more slow moving, and the beta waves are much more, they have a much shorter period. And so that is then translated here by that going through this diode on each one and being turned into a DC value. So then to give you an example of how this would change if the composition of the waves inputted changed, if we go to the wave that I'm generating, and this first one here, this sine 18 pi x, that's a wave with a frequency of 9 hertz. And so if I make the amplitude of that smaller to say, well, now there's less of that wave in the brainwave, then I should expect the output of my circuit to show a dimmer white LED, and that is what we see here. The LED for white is now super small because I made that very small, and then it has ranges in between. As you increase the amplitudes of the different components, then their output should change. So that circuit now shows that the value of the alpha waves has changed, and the beta waves though is still the same. So you still have this same beta wave composition but a different alpha wave.